In the nanoscale world, there are characteristics that cannot be imagined by common sense. To lead the way to new nanoelectronics, it is necessary to measure these characteristics correctly. However, conventional testers are of course too large to measure nanoscale structures correctly. Thus, the research team began working on developing a nanotester that uses STM tips as electrodes. The apex of a conventional STM tip has a radius of about 50 nanometers, and therefore two STM tips can measure a minimum distance of 100 nanometers. The research team overcame this issue and successfully created a double probe STM by growing a nanorod with a 10 nanometer radius at the tip of the STM. The double probe STM is used to measure electrical resistance of carbon nanotubes. The two STM tips are put into contact with a carbon nanotube, and then the distance between them is gradually narrowed. Electrical resistance occurs when electrons passing through materials are scattered by impurities or atomic vibration. Therefore, as the distance becomes shorter, electrical resistance becomes smaller. However, measurements show that electrical resistance definitely becomes smaller as the distance decreases, but that under 470 nanometers, electrical resistance is the same. So, what is happening here? Under a certain distance, they observed ballistic conduction in which there is no scattering of electrons. In the graph, there is still resistance value because of contact resistance with the measuring instrument, but the actual internal electrical resistance is essentially zero. In this way, the research group successfully observed ballistic conduction in a carbon nanotube and accurately measured the electric conductivities of various nanowires. Based on the double probe STM technology, the project began to develop a quadruple probe STM for the purpose of cancelling the contact resistance. The project used extremely sophisticated technology to control and coordinate 4 probes at atomic scale precision to finally realise a quadruple probe STM. Using the quadruple probe STM, they attempted to measure the electrical conductivity of C60 thin film. C60 thin film is an insulator that does not allow electricity to pass through. However, when an electron beam is projected onto the surface, molecules are polymerized and the material becomes conductive. So the question is, how conductive is it? Unfortunately, because nano-sized cracks are generated, the electrical conductivity of polymerized C60 thin film cannot be measured using conventional methods. The quadruple probe STM can measure electrical conductivity inside a domain where there are no cracks. As a result of measurement, it was found that electricity flows better in polymerized C60 thin film than expected. At room temperature, polymerized C60 thin film becomes a conductive material, like a metal. The project discovered an epoch-making application of polymerization. The STM tip can polymerize an area, and if the polarity of the voltage is reversed, polymerization is broken and the area returns to its original state. Moreover, it is possible to polymerize the same area again. Thus, a new memory function was discovered. The challenge of this project was to increase the recording density of memory to the maximum possible limit. As a result, they succeeded in fabricating memory bits as small as 2 to 3 C60 molecules. If this memory is realized, data can be stored at about 40 terabits per square inch, the size of a $50, enough storage to hold the equivalent of about 10,000 DVD quality 2-hour movies.